Okay, well, thank you all. So this is really some essentially an uncertainty analysis that we've done on the data from the SOAS study. And so it's with a student, Phil Feiner, Li Zhang, and David Miller, who did a lot of the analysis that we have here, and of course to many, many SOAS colleagues who have contributed to this work. So here's really the problem here, and that is that, and I think this plot does it very well. So this is the idea of a recent paper that says there's a maximum efficiency in hydroxyl radical-based self-cleansing of the troposphere. And so these are several studies that have been done over the last decade or more. And just the important plot is this one here, which is, let me explain how this is produced. So basically, we have all these different environments, and the way that you can get these data are, you pick a typical day for each one of those environments. So the amount of sunlight will be different, the amount of VOCs will be different and whatnot. And then in the model, what you do is you just change the amount of NO2 in this case, really NOx. And then this is a model-derived line here. And then, of course, they're all very different. And so what you do is you normalize them so that you find the peak in OH, and then you normalize that to 1 for each case. And so each one you bring it down to 1. And then for NO2, you say this is the NO2 at the peak of OH, and so you normalize the NO2. And by doing that, you can put all these different data sets from very different places on one plot, which is kind of a nice idea, and I think it mostly works. And so the point is that what you see here is you see on the high NOx side, where this would be urban areas typically, that you see that the measurements, which are from cities like New York and Mexico City and whatnot, kind of line up along it. But when you get to this side here, the values aren't falling off as we expect, which is the blue line here. They're mostly staying high. So this is this idea that there's some sort of mechanism that's keeping OH high in low NOx environment, high VOC environments. That's the idea. So what I put is stars on all the ones that are from the measurement from my group over the last 15 years or so. And you see that we're up here, and then there are all these measurements up here from various regions in Southeast Asia, and forests, in northern South America, and some in China. And then there's one outlier down here, which is our measurement from Bearpex, which was in California forest in 2009. So this is really the conundrum: is OH up here, or is it down here, and do we really sort of understand what's going on? And so we're not really going to answer that question today, but that's really the problem that's out there. Okay, so our measurements for SOAS are shown here. And so the model that we've run, which is a Rackham mechanism, but we've added Isoprene specifically to it as we have monoterpene chemistry. So they've been separated out. And this is the model that we used for the Bearpex study that Jing Mao put together. And so here's the modeled OH, and this is sort of average for 9 days where we had all the data. And then here's the measurements here. And then here's HO2, and you see here's the model and here's the measurement here. And so there's a very big difference in that. And so the question is, what are the error bars on these things? And you know, are they really different or not? And so in this case here, this is roughly what we would say the uncertainty of the measurement is. And the question is, what is the uncertainty in the model? Are these really about the same? Now, to see more about these measurements, you should see Phil Feiner's poster at this afternoon. And here's the number here. Okay, so the idea here is we're going to look at these uncertainties. What is a good estimate of the model uncertainty, and which model inputs really are influencing the modeled OH and HO2? Now, by modeled inputs, what I mean is not only sort of the concentrations that go into that model to constrain it, but also the rate coefficients and the yields and actually the deposition rates. All those are factored in here in this analysis. And so the way we do this is with this random sampling high-dimensional model representation. And we use software by Aerodyne here. And the idea is rather simple. And what you do is you take all your inputs, of that rate constants, yields, concentrations, deposition rates, and you have your base case, and then you randomly vary these over the range of the uncertainties that's listed for each one of them. And then you run the model and you get your value. And so, for instance, if you do all of these here, maybe this is what you get here on this distribution. And then you do this 10,000, 30,000 times. And so you end up getting a distribution here of possible values. And then you can use this information and you can create orthogonal polynomials for whatever you're interested in an output, and you can say, okay, what is sort of the polynomial of inputs that gives me this output? And from that, you can look at variance, and then you can derive an uncertainty, a sensitivity. And so that's what's being done here, is to derive a sensitivity. And the nice thing about this high dimensional effort is that you're varying them all at the same time, so you can look at essentially coupling between inputs and what their impact is on whatever you're interested. And of course, for us, we're interested in OH and HO2, and so that's what we've done for the model outputs here to look at. Okay, so just to show you, of course, you could run the whole day, but it would take forever at 30,000 runs of the model for each one. And so instead, we've chosen 4 times, which represent very different periods during the day for SOAS, where here's one at high NOx, and here's one more midday, and here's evening, and then here's, of course, night. It's right here. Now, today, in the interest of time, I'm just going to show the midday values just to show you what it looks like, and then I can talk to anyone about what the other time periods, how they're different from what we get here. And just to show you on the OH and HO2, here's where these 4 time periods are and where they fall, and you can see they're very different in terms of the HO2 and OH behavior. Okay, so we do this, and the first thing we can get out is a sense of what is the model uncertainty for OH and for HO2. And so here are the distributions for OH and HO2, and what we see is we see a typical uncertainty is somewhere in the low 20s% to high 20s%, and that's sort of 1 sigma uncertainty. So it gives us an idea about what this box model, and really what other box models we've tried, can do, and that's about it. That's your limit. And so if you consider sort of 2 sigma uncertainty, we're talking sort of 50%. A factor of 1.5 is about the best that a box model can do. And so that's interesting. It tells us, how big our error bars should be on that other plot. And we will see in that case that for the case of OH, we can't say that they're statistically different between the measurements and the model, but HO2 is clearly different. Okay, so here's an example of the sensitivities. And so this is for OH, and so I've grouped these sort of by function, if you will. And so when you look, you can see that the isoprene chemistry is almost half of the total. And so the kind of things that Paul and Jenny are talking about are really important to get these right. And the interesting thing is these are sort of first steps even in the mechanism. This is isoprene proxy radical here is what I mean by iso up here. And you can see that that's really very, very dominant. And then there's a class with NO that's in there. And finally, this is primary production that's up here. And then the other up here is a combination of all the things that are, say, less than 1% of the total, and a little bit, maybe 8% is really second order stuff. So we see that mostly this is by first order. We can do most things by first order here. Over here I have the uncertainties that we use in order to put into the model. And you see even those things that are known to 10%, that's really not good enough in some cases, which is kind of interesting. Now for HO2, we see that essentially the proxy radical, isoprene proxy radical reacting with HO2 and NO is dominant, so it's over half. And if you include the yield here of HO2 that comes out of this, it's 2/3 of the total. And so what that says is we really need to pay attention to what's going on there. And then you see the rest is really, once again, primary production of HO2 or of OH. And the photolysis of JO singlet D is really big here. Okay, so just to put this on a plot, to show you sort of in the isoprene, so this is an important step, even though it's known to 20%. And then these are very important steps. And then the yield of HO2 down here is a really important step as well. So all of these things need to pay a lot of attention to, and it sort of amplifies the comments that Paul was making earlier about sort of the importance of this chemistry and getting it right. Okay, so now what I've said is this is preliminary work, because when you do these sort of analysis, you're never quite sure that you've done them right. And so the only way to get around that is to do many things many different ways. And so some of the changes that we have to make, for instance, we have to pre-screen the input values, because in the model, the number of input values that we put in, if we did every rate constant, every yield, is 1,600. And so you have to do sort of n squared runs divided by 2 in order to get enough data. So you can see that would, I wouldn't be here now if we were doing that. So we have to do pre-screening. And do you do the right pre-screening, and have you eliminated some things that you shouldn't eliminate? So this, we played around with some, and we think we're in pretty good shape, but we're going to do this more. The estimated input uncertainties, you can see how important that is. And so sometimes it can make a difference, and sometimes it can't. And so, and then the uncertainty distributions, what is that distribution? Because you're choosing randomly over a distribution. And then the number of runs, and then to use a different model. So the next model we're going to run is MCM, for example, to see if we get any difference. So what we've found from previous work is the influential parameters are not likely to change very much, but the fractional sensitivities almost certainly will. Okay, so what do we have? Well, we have the measured and modeled OH certainly agree within the uncertainties from what we see. Although the HO2, that's a problem, and so see Phil's poster and talk more about that. The model uncertainties are really at 1 sigma are really quite high in some sense, and so that really should be reduced. And by the sensitivity analysis, we see where we should attack first. And amazingly, so it's in the isoprene chemistry, it's in the Hox-Nox chemistry, which is fairly well known, but not well enough. And it's in the primary Hox production. Now, one of the things that's been happening in field studies is we've not always been doing a really great job on measuring the photolysis frequencies. I think we have to start doing this if we're interested in measuring the photochemistry and what's going on there. And the NO is sometimes not measured very well either, and that's just a crime in some sense. And so we need to fix that as well. And so we have further analysis underway, but we'll show the other time frames because they're slightly bit different, but it's basically the same ideas. So thank you very much.
Thank you, Bill. We have time for questions. Yes, debate.
Bill, I mean, to dig a little bit deeper, does the temperature dependence matter a lot? You looked at grade constants important, getting isolated in the temperature dependence of these grade constants.
We did not adjust the temperature dependence for these runs, and so I can't answer that. But that's something that we will do when we do the next level. Yes.
Ron.
Really, an awful lot of your experimental error cancels if you look at the ratio of HO2 to OH. So you put that in this analysis and try and deal with that, do something that constrains things a little better?
We've done that. We haven't done that for this data set, but we've done that for previous data sets and have looked at that. And you end up with I mean, that's just taking out the experimental, so it's not really addressing this model sensitivity. But you mean in terms of agreement or disagreement?
Well, yeah. It takes out a lot of experimental uncertainty, so you can focus, and it takes out a lot of the model, a whole bunch of different model parameters control that ratio, perhaps.
We find that the Hox-Nox still is dominant for both of them, and it doesn't really cancel out even in the ratio. It's still important. So, yeah.
Let's get one more question, Glenn.
Oh, yeah, Bill. I was just wondering if your HO2 measurements have been corrected for any RO2 interference.
We've run it so that they're very minimal for this. So we've figured out, like everyone else, how to do that, and so that's what these data are. They are quite free of RO2 according to the laboratory.
Thank you, Bill, again.